Okay. Okay, so we're going to take these two vectors right here, and we're going to find the projection matrix for these two vectors, okay? And what is this thing really going to project upon? This thing is going to project onto the xy plane, because this just has an x value as 2, 0, 0, and this just has a y value of 0, 3, 0. So this is going to take any vector in R3 or in three-dimensional space, and what is it going to do? It's just going to slam it down onto the xy plane. That's what we're trying to achieve, okay? Okay, so just like in the previous problem, the very first thing we do is going to be A transpose A. Okay. So let's do that. And so we're going to say A transpose A. Okay, so this would be 2, 0, 0, 0, 3, 0, and this is going to act upon 2, 0, 0, 0, 3, 0. Okay. And so what does this thing come out with? 2, 0, 0 acting upon 2, 0, 0. That's going to give me about 4. Okay? Now 2, 0, 0 acting upon 0, 3, 0. What is that going to give me? That's going to give me just a 0. Now 0, 3, 0 acting upon 2, 0, 0. Well, that's just going to be 0. Now 0, 3, 0, this guy right here, now acting upon 0, 3, 0, that's basically just going to be 3 times 3, which is going to come out to 9. Okay. So that's the very first step of the problem. Step 1, just A transpose A. All right? Okay. So that's step 1. Now step 2 is to find the inverse of A transpose A. Okay? Okay, so we have 4, 0, 0, 9 augmented with the identity matrix. Okay, so we have A transpose A and the identity matrix, and then we're going to go through those normal steps like we were doing before to get the identity matrix onto the opposite side of the problem. Well, for this problem, we have 4, 0, 0, 9, okay? Well, to get the identity matrix on the opposite side of the problem, I just need to divide the entire top row by 4, okay? So, what would that give me? 1, 0, 0, 1, 0, 0, 1, okay? And so, when I get the inverse of this, this would be 1, 4, 0, 0, 1, 9. So this would be A transpose A inverse. Okay, so we found the inverse of A transpose A. Okay, great. Now we're going to go to the next step, which is going to be A transpose A inverse A transpose. Okay. Two, 0, 0, 0, 3, 0. Okay. So that's our original A that we were dealing with. Okay. And then we have 1, 4, 0, 0, 1, 9. Okay. This is A transpose A inverse. Okay? So now we're going to multiply it by A transpose. So A transpose would be 2, 0, 0, and then 0, 3, 0. Okay, so 2, 0, 0, 0, 3, 0. Okay, now this is going to act upon, let's have this matrix right here, A transpose A inverse, act upon A transpose. So 1/4 0 is going to act upon this thing, and so that would be 1/2 right there. And then acting upon that one would just give us 0, and that one acting upon the third one would just give us 0. Now 0 and 1/9 acting upon this thing, so 0, 1/9 acting upon that one right there would give us a 0. Now 0, 1/9 acting upon 0, 3, that would become 3 divided by 9, which would be 1/3. And then 0, 1/9 acting upon 0, 0 is just going to give us a 0. Okay. All right. Now we're going to have A act upon all of this. All right. So all right. So 2, 0 acting upon 1/2. 1. And then 2, 0 on 0, 1/3. That's just going to give us a 0. And 2, 0 acting upon the last one is just going to give us a 0. I'm going to make this a little bit bigger. Okay, now 0, 3 acting upon 1/2 0. That's going to be a 0. Okay? Now 0, 3 acting upon 0 and 1/3, so that's 3 times 1/3. 3 times 1/3 would just be a 1. And then this would be 0. Now we have 0, 0 just acting upon everybody. All of this is going to be zeros. So that would be 0, 0, 0. Okay, so in case you didn't fully see that, it's 1, 0, 0, 0, 1, 0, and 0, 0, 0. This is the projection matrix for the xy plane. And think about it, it doesn't matter what type of vector you choose, what's going to happen, it's going to, I mean, you can have this matrix act upon either one of those, and they're going to stay the same. But if you have any vector that is not within the xy plane, then this matrix, what's it going to do? It's going to kill the z component, okay? And actually, if I pick different numbers besides 2 and 3, I still end up with the same matrix, okay? Didn't matter what numbers I picked for those components. I basically said, I have a vector in the x direction, I have a vector in the y direction, and then what would be the projection matrix onto that? Well, what does it do? It kills the z component. So if we want to have a look at this, what is this thing really doing? So let's say we had some vector okay, so this vector, and if you can't see it, that's 1, 2, 3. It doesn't matter what I pick. And now let's have this matrix act upon 1, 2, 3. So alright, so we're having the projection matrix act upon 1, 2, 3. And what is it going to do? 1, 2, and 0. So you see that it just basically it knocks off the z component, and so that's the projection matrix for the xy plane. And you can have other projection matrices for the yz plane, the xz plane, And they basically form different things like this, but your zero would just be in a different spot. So if we were wanting to project something onto the XZ plane, what would you basically be doing? You'd be killing the Y component of the problem. So what you would end up with as your projection matrix for the XZ plane, it would be a 1 here, a 0 here, and a 1 here, meaning that it would keep the X component and the Z component, but it would destroy the Y component. It would send the Y component to 0 because in the XZ plane, Y is always 0. Okay?